This video provides a brief introduction to the Debye Law of heat capacities and how it's connected to the calculation of absolute molar entropies. Alright, in prior videos we have seen that the determination of absolute molar entropies at 298 Kelvin and 1 bar can be achieved with a graph like this that is based on the third law of thermodynamics. Right, so the idea is that for perfectly crystalline substances at 0 Kelvin, the absolute molar entropy according to the third law is 0. And what that means is that if you want to determine what the absolute molar entropy of a substance is at any temperature of your choice, typically 298 Kelvin, then what you have to do is simply track how the entropy grows. As you heat the solid, then that solid might undergo fusion, then you heat the resultant liquid, maybe the liquid vaporizes, and then you have to heat the gas until you get to your 298 Kelvin. Okay, so generally this is done at constant pressure, so we can write here 1 bar and put there your standard conditions. Now, something that is important in this graph is to consider the fact that for all of the heating steps in the solid, liquid, and gas, you actually need to know what the heat capacity of that substance is, all right? Because the change in entropy for a particular heating process or cooling process is just the integral of the heat capacity over T differential of T, right? So you actually need to know what that heat capacity is in order to be able to trace these lines, okay? So notice that generally we're interested in molar quantities. That means that these are going to be per mole, and if we're working at the constant pressure conditions, that is going to be your constant pressure heat capacity. Right, so again, the question is, do we actually have the values for the heat capacities for any substance under any condition of temperature that we need to trace these lines? Well, for gases and liquids, that is not very hard to do. For solids, it's also relatively simple, unless you're going to really low temperatures, right? So we're talking about this part of the curve where you're getting to really low temperatures close to 0 Kelvin. A problem here is that when people were starting to think about absolute molar entropies, that was perhaps 100 to 120 years ago. And a problem is that 120 years ago, we did not have instrumentation to go to very low temperatures, say 4 Kelvin, 5 Kelvin, 10 Kelvin, with ease. We just didn't have things that got that cold. And what that means is that we actually did not have a way to determine what these heat capacities were really close to 0 Kelvin, right? And that means that, well, if you don't know how this curve grows in this region, then you're going to have some error determining what the absolute molar entropy is at the temperature that you want, which is, again, generally 298 Kelvin. Right, so because they couldn't do any experiments, they didn't have the instrumentation necessary to determine those very low temperature heat capacities, then scientists had to rely on models. And Debye's law of heat capacities is just a model that allows you to figure out how that heat capacity looks like really close to 0 Kelvin. So after some study, Debye, who became a Nobel Prize later on in his career, okay, said that the way that the heat capacity for a solid depends on temperature is just a constant A. Let me write that a little larger. Just a constant A that depends on each substance, and it follows a cubic relationship with temperature. And again, this is specific to the substance. I'm simply going to write here what the value would be for diamond. Okay, that is 3.02, 10 to the minus 7. And the units are going to be such that this is joules per mole per Kelvin. That is Kelvin Q, right? So that needs to be joules per mole, Kelvin to the 4th. Okay, so that you get a joules per mole per Kelvin here. All right, so and the way that Debye found this cubic relationship was by simply thinking about what happens to a crystal, right, to a solid substance that is crystalline, when you start to add energy to it as heat, right? How does this solid absorb that energy that you're transferring? What Debye thought is that this energy is going to be absorbed in terms of vibrations of this crystal. But something that was quite new about Debye's idea was the fact that when you think about these vibrations in a crystal, those vibrations are not going to be confined to just a few atoms, perhaps a couple of atoms right at the surface of the crystal that are going to undergo vibration. Instead, these vibrations are going to be localized throughout the crystal, and they're going to be called phonons. Right? So again, that was kind of something revolutionary at the time, that using that phonon, the localized vibration concept, he was able to deduce this cubic relationship of the heat capacity and temperature. Later on, we were actually able to get things like liquid helium and other instrumentation that allows you to go to really low temperatures. Then we were able to see that this model actually is correct, right? So you do have a cubic dependence of the heat capacities on temperature at low temperatures for crystalline substances. So then a question is, well, can we use this in an applied example? And yes, we can, right? So what we're going to do here is I'm going to show you how you can use this law of heat capacities to determine the molar entropy of maybe diamond at 10 Kelvin, right, at a temperature that is very low. The range of applicability of this law is typically 0 to maybe 10, 20 Kelvin, thereabouts. Right, so what you would do then is take this heat capacity law and just replace it there, right? So you would write that this is going to be equal to CPM. Again, if you use here the Debye's law of heat capacities is AT cubes. All right, but of course you can cancel the denominator and make it AT squared. And you can factor out that constant, which is again a constant, and you just have a fairly simple integral to solve. All right, so then we can here say, well, the change in entropy, molar, and again we're going to do this maybe from 0 to 10 Kelvin, is going to be equal to the integral from 0 to 10 Kelvin of this t squared differential of t. Okay, but of course that integral happens to be a t cubes over 3, and you have to evaluate this between 0 Kelvin and the temperature that you want. Again, this temperature might be 10 Kelvin if that's what we're doing. We're just going to leave it generically here, but again, here's where you would plug your target temperature. Okay, so notice that this is simply going to be equal to a t cubes over 3 minus 0. Okay, so we're not even going to just write that. So that is actually the result of that integral and the evaluation of the limits. But again, notice that this is actually very similar to the heat capacity at constant pressure. As a matter of fact, this is simply Debye's heat capacity at constant pressure divided over 3. Okay, so again, if you want to calculate what the absolute molar entropy for a substance is at 10 Kelvin, then you would simply have that. Notice that this change in entropy is simply the entropy, the molar entropy of that substance at 10 Kelvin or at a temperature T minus the molar entropy of that substance at 0 Kelvin. Okay, but of course the third law of thermodynamics tells us that this number should be 0. So when you're doing this calculation, you're calculating directly what the molar entropy would be at the temperature of your choice, right? So again, the only thing remaining here is just to find out what the value of this A is, which again for substances is known, right? So that would be the one for diamond. And then just plug in here your target temperature, 10 Kelvin, right there, and then you will be able to calculate what your absolute molar entropy is really close to 0 Kelvin. Okay, great. So let me summarize this video. We have provided a really brief introduction to Debye's law of heat capacities. We have not seen how to derive that, but we have seen how you can use it, how you can apply that law to calculate absolute molar entropies of pure substances at temperatures that are very close to 0 Kelvin.